Good day, everyone. Today we have our next webinar in Solver colloquium talk. And today we have Dr. Robert Allen, who graduated in 2017 from the joint UTSA Southwest Research Institute graduate program and is now a staff scientist at the Johns Hopkins Applied Physics Lab. His research interests span from magnetospheric plasma sources and instabilities to solar wind particle acceleration. He is currently the instrument scientist for the Solar Orbiter Suprathermal and Spectrograph Sensor, a member of the Parker Solar Probe Project Science team, and a member of a SWIP and ISOIS instruments teams. Relevant to this talk, he is also a PI on a heliophysics mission concept study, HelioDisk, which aims to understand the mesoscale structure and dynamics of the solar wind. So, Robert, please go ahead. You have your 45 minutes. And I will give you a warning 5 minutes before the end.
Wonderful. Thank you, Gregory. Yes, so I'm here to talk about the Heliospheric Distributed In Situ Constellation, or HelioDisk mission concept. And so this is one of 8 studies that were selected by NASA to be studied kind of as a pre-decadal feeder of mission concepts. And so the idea for this is we're aiming for a mission concept that would be in the Solar Terrestrial Probes class of mission. So kind of this large scale structure missions to study the fundamental nature of heliophysics. And so this mission in particular is a mission to untangle the dynamic mesoscale Sun-Earth connection. Okay, so mesoscales really do form this critical gap in our current understanding of heliophysics. And so across all of space physics, mesoscale structuring and dynamics has been this critical gap in our understanding and in our observations. So in the context of the solar wind at 1AU, mesoscales can range from the hundreds of RE to a few degrees in heliographic longitude, or in other words, kind of the spatial temporal scale sizes and dynamics bridging the gap between the large scale persistent structures in the solar wind and the microscale kinetic processes. And the mesoscale structures, therefore, really are not well captured by observations or models that we currently have. And so really kind of to illustrate this on the figure down below, we have, a lot of these kind of WSA Enlil type models and our current HSO conjunction. So when you want to compare Solar Orbiter Parker Solar Probe observations, you can really kind of dive at these more large scale persistent macro scale structures that exist in the solar wind. And on the other end of the spectrum, when you go to the micro scales, you can look for a lot of these kinetic dynamics that happen using either times when MMS is in the solar wind or when clusters in the solar wind, or comparing between the L1 constellations or the potential Helioswarm mission that might be upcoming to really kind of dive at some of these smaller scale variabilities in the solar wind. But what we're going at for this mission is kind of this bridge in between that really has been elusive from our observations at this point. And so we would want to be starting kind of at that upper end of the microscales and then gradually span out to look at this mesoscale dynamic range. And as we do that, we have 3 main science thrusts. So our first thrust is to fundamentally try to explore the structure of the solar wind on these scales and what effects that has on transients. Our second is to explore the effects of those mesoscale structuring on and variability on particle acceleration. And then lastly, we want to look at the effects that would have then on particle transport. So before kind of jumping into our science motivation, I did want to have kind of one slide to kind of look at the mission at a glance. And I'm going to kind of double back at the end of this presentation to go more in detail about the mission architecture as we're envisioning it. But this is just to kind of set the stage as we go into our science motivation to understand how we're kind of thinking about going about this. So what we kind of arrived at is in order to explore the mesoscale structure and variations of the solar wind and subsequent effects on particle acceleration and transport, we really do need multi-point observations with small inner spacecraft separations. And so what that's led us to then try to envision is having a set of 4 spacecraft that are in Earth trailing heliographic orbit. And so if you were to think of the Earth being here, so be flipped, of course, this kind of be behind the Earth vantage point. then we'd have the 4 spacecraft spread out, in an Earth trailing orbit behind the Earth, but still going around the sun at 1 AU. And we'd put them such that they have relative drift rates from the Earth that are slightly different between each of the spacecraft. And so at the very beginning of the mission, you'd be, on the order of 100 RE separation between each of the spacecraft. And then as the mission goes on, they'd slowly fan out and spread out, such that by the end of the mission, you'd be spanning a few degrees in heliographic latitude or longitude, sorry, late in the mission. So really what that allows us to then do is be able to sample the solar wind at all of these scales in between, which is really critical for the science want to do, is not just targeting a single scale size. And so what that would mean is, if you have a CME structure, not only could you see kind of across that structure, so you could look at how you're connected to different parts of the structure, and as it comes by you, actually look at variability across that CME structure, but also then drive at questions such as the flux tube structuring in the solar wind. So with this kind of very basic architecture in place, we then have kind of our left side STM here. And so again, like I said earlier, the overarching goal we're going at is really an investigation of the fundamental mesoscale nature of the variable solar wind and impacts that has on particle acceleration, evolution, and transport. And so our goals then are structure, acceleration, and transport. And so from this, we've now flown down into a series of targeted science questions. In this talk, I'm going to be calling out just a subset of these. And so I'm going to be kind of talking about the motivation for the ones that I have circled here, as well as one bonus science topic that I think is relevant for sulfur, but isn't exactly necessarily one of these, but one that we could address. So with that now, I want to start stepping through each of these one by one. So we're starting with our science thrust dealing with structuring. And so we know that the solar source of the solar wind does have small scale variations. And so you can think of your granule, supergranule variations on the solar surface. And as such, we know that the initial solar wind should have this mesoscale structuring as well. And as these structures then convect out to 1 AU, we do know that they will undergo various processes such as expansion and stochastic meandering, but they still may preserve some of these characteristics as either granule or supergranule relics of the sun. So kind of imagining your solar surface as this variable surface, then as you float out, if you were to take this cross section kind of a sphere at 1 AU, you could imagine kind of having this stained glass kind of mosaic of flux tube bundles. And looking kind of along those flux tubes, you might have this more spaghetti picture, these intertwining flux tubes that give you some of this more complex variability we have in the solar wind. But for a lot of these, from a single spacecraft point of view, it's really difficult to start detangling what the structure might be. And so as a result, the nature of flux tube structuring at 1 AU does still remain an open fundamental question that we have in heliophysics that really can only be addressed when you start approaching this from the standpoint of multi-point observations with small spacecraft separations to actually start sampling where these flux tube structuring starts breaking down and how rich are these boundaries, how fuzzy are they, and how large really are these flux tube bundles. Going beyond that, we also know that the origin of the injection range variations we see in the solar wind is not well understood, nor is the breakdown between our injection range variability and more our inertial range variability. So this kind of break in the distribution. And this is really important because when you think of this large scale range, this is where you have those more persistent, almost static-like structures in the solar wind that we think of when we try to have that 0th order picture of what any part of the solar wind looks like. And then, again, we get down to the dissipation range, you're going to those smaller scale physics, but kind of these breaks in the distribution are not really well understood of where you get that breakdown. And one of the issues we have is from a single spacecraft observations, we can't really distinguish between temporal variations or spatially variable variations that are flowing over the spacecraft as the solar wind convects across it. And so, you can, use things like Taylor hypothesis and various things like that in order to tell yourself that what you're seeing is one or the other. But if we really want to drive after this in a very robust and rigorous way, we really do need these multi-point observations with these different spacecraft separations to approach this from a purely spatial standpoint, and that will allow us to kind of start separating out the spatial temporal variations. And so for the mission we're envisioning, we would span most of, if not the entire inertial range, and span this break in the distribution later in the mission, and then kind of go into the injection range more so in extended mission. I should say, even though we have a hard line for the start here, of course, most of our commissioning happens before that. So we'd have a rather interesting wealth of observations during the commissioning phase of that breakdown between the inertial and dissipation range. And so there's a lot of science we can do upon just better understanding the fundamental nature then of the solar wind variability. The next thing is, once you kind of have accepted to yourself, okay, we have this mesoscale variability in the solar wind flux tube structures and variations in solar wind speeds and densities. We have this variability from turbulence. The next question is, what impact does that then have when you start imposing large scale structures on that? And so, for example, if you were to have a CME expanding out into the solar wind, that solar wind itself is variable, then that should then instill variability across that CME structure. And so the few studies that have investigated mesoscale structuring of CMEs have found that CME shocks and magnetic ejecta do have this smaller scale structuring, and that the energetic particle profiles often change over mesoscales. And so from that, if you were to look at this paper here, you see that relevant scale lengths, not only are they of mesoscale sizes going throughout this, the scale lengths actually do vary depending on where you are within these structures. And so a mission targeting only a single scale size really would not be able to capture the wealth of scales that are relevant for these different structures. But also, what's really been interesting is the Neugebauer paper in 2006, which compared ACE and wind observations when they were very far apart comparatively to where they normally are, found that if you look at the time intensity profiles of energetic ions at these shock structures, you quickly see that by the time you get up to hundreds of RE, they don't necessarily match up very well anymore. And so really it's, when there is this variability that does seem to be then affecting that particle population associated with these shocks. And so there is this larger variability, not only in the structure, but also in the energetic particle content. And so what these observations then tell us is that this kind of large scale only viewpoint of these smooth structures expanding into the solar wind really is an incomplete picture of the fundamental structure of the solar wind and important processes that define its evolution. And this really does have implications even when you want to drive down into solar wind magnetosphere interactions of, while the geospace system might be very small in this setup, if you do have this variability across, then how can you really take any observations we have and know what's going to reach the Earth? And so it does have larger scale implications when you want to flow down the system in kind of the system science tree we have. But so for this, then what we say is, really again, a dedicated multi-point observations are needed to better constrain variations within these structures. And so having our multi-point observations at these different scale lengths across these structures and being able to build up this more complete picture of what the structuring of CMEs and other transient structures might look like on these mesoscales then becomes really critical. So then that kind of drives us, as we kind of elucidated in the last slide, into the idea of particle acceleration and the energetic particle content associated with these structures. So what we do know is that radio wave observations have revealed that shock structures can vary on mesoscales. And so the Bale et al. And a series of papers that followed after this using radio wave observations have shown that when you fly a spacecraft through these structures, you can see evidence that there are kind of these bumps and lumps on these structures. And that then, of course, will change acceleration happening locally within those bumps and lumps. And so where we kind of are today is that while current models can reproduce the large scale variations in event integrated particle spectra along an interplanetary shock, these approaches really are unable to capture the effects of mesoscale structuring on shock acceleration for short time cadence or evolution of the particle populations themselves. And so if you were to think about kind of, you have this nice model of a CME going out, you're able to then compute these event integrated spectra, and they do pretty well, particularly in the higher energies. But if you were to actually fly spacecraft through this structure, then one might assume you would start seeing variability within the time intensity profiles. And so, as I said, for example, the event integrated spectra do pretty well along, and part of that is because especially when you get to higher energies, you really are sampling particles that were accelerated across a lot of that shock structure. But when you start getting into more the superthermal range and wanting to look at seed particle populations or freshly accelerated particles, that's where you do get a lot more of this localization, and that's where we really haven't been able to really reach with a lot of our simulations. And so understanding the role then of mesoscale structuring and variability of particle acceleration associated with interplanetary shocks then is critical for really investigating the causes of observed variations we have between different events and potential variability in seed populations. So as far as a bonus topic we can go, because this doesn't actually necessarily fit into one of our science questions per se, is from this constellation, is there anything we really can then backtrace back to what coronal physics and what might be happening there? And so Gang Li had come out with a paper in 2020 using wind observations that found that the injection timing for flare-associated interject electrons compared to the hard X-ray observations seemed to suggest the presence of two distinct electron populations in an impulsive solar interject electron event. So what they did here is that these data points on their figure is showing the dispersive timing of different energy particles of the interject electrons. And they found that assuming a path length from the source out to wind of 1.5 AU led to the data points aligning in a very nice dispersive signature. And this seemed to indicate this is the most likely path length for the particles, whereas if you start varying your path length, you started getting more discrepancies. And so it seemed less the correct way of looking at the particles. But when they did this, what they found is that then the injection timing for the interject electrons that flew out into the solar wind seemed to be occurring prior to the hard X-ray observations from GOES, which is the green line here. And how they interpreted that is that because your downward going electrons is what gives you the hard X-rays, this almost seemed to indicate that whatever processes were happening in the corona were releasing those interject electrons first out into the solar wind, and then as a secondary population down further down in the corona to give you those hard X-rays. And so the presence then from their paper, they said the presence of these different interject populations seem to be able to possibly be indicating some kind of different reconnection modes occurring. And so depending on if you have interchange, reconnection between closed field lines, you might be able to get different timing in the release of particles either downward or upward. But really, as I kind of pointed to, the main kind of fudge factor in this study that you have is that determination of path length. And so if you assume a different path length, you get a very different start time for these interject electrons. And so the robustness of being able to do this analysis then really depends on how robustly you're able to define what your path length is to that source. And so really for that, because we know there is this mesoscale variability happening in your flux tube structures and your magnetic structures, what we really do need then is to, as we wanted to do in earlier questions, better understand what the actual structure is for the solar wind on these scales. And so for that, then what we're saying is that observing interject electrons in multiple spacecraft with a constellation that stands within about 10 degrees, which would be within what you would expect ambiguity to be from stochastic field line motion. That would then allow us to deduce the acceleration timescales better. We have a better handle on that propagation time frame and be able to more robustly say, okay, when were these particles actually released from the sun? And how does that then compare with X-ray observations for the flare site? And so from this then, new multiple observations of mesoscale separations at 1AU might actually be able to better provide us insight into different flare-related processes happening within the corona. And so, really getting a handle on this allows us to better understand how our observations further out in the heliosphere might be able to elucidate processes happening closer in. So then that, of course, brings me to transport, which is very relevant to the previous question. And so, as I talked about, we know that various processes happen between the sun and an observer. And so we know that field line meandering and or stochastic motion can lead to uncertainties of where a source region may map to. And several studies have pointed to stochastic motion giving you an ambiguity of about 10 degrees in longitude at 1AU. And we also know that processes like cross-field diffusion and other transport processes can be poorly understood in the solar wind. And one example of why that could be is that it's currently unclear how much of what might be interpreted as cross-field diffusion previous observations might actually be a result of things like philae meandering or stochastic motion. And so if you were to take, an SEP event and take several observatories that span, 30 degrees in longitude, and you see everyone sees some electrons, and you try backing out, okay, well, how much of that is from those particles just having cross-T diffusion versus how much of it might actually be that these field lines themselves are not mapping where you think they're mapping. It might, randomly move, and so maybe that then is giving you more your diffusion. And so from that, then it's really fundamental to understand. We want to understand then the transport of these particles is to understand these different terms we have. So for that, then what we would like to do is actually be able to go through and say, okay, well, if you were to have this stochastic motion leading to the field lines reaching out in this manner, is actually take multi-points throughout this range of 10 degrees in longitude, and then be able to reconstruct, okay, what is your distribution of particles? And from that, can we start then pulling out information on either the extent or variability of stochastic motion depending on solar wind type? And so to do this, we would argue that really only a multi-spacecraft point of view of these mesoscale separations would give us the needed measurements in order to really constrain some of these problems. And we do know that things are a bit more complicated. And so one example was from the Klassen et al. 2016 study using stereo observations when stereo was on the other side of the sun as Earth. And in this event, they were looking at this really impulsive SEP event. And what they found was that they reported that in this flare event, the active region were near the foot points of stereo, but the observations indicated different activity than you would expect. So in this event, they say that the flare that led to this SEP release happened here, whereas it would have gone off in this direction. And so as you see, both from just simple Parker spiral paths, as well as where the foot points should have mapped to, you would have expected stereo B's foot point to actually be closer to that source of energetic electrons than stereo A. But when you actually look at the localized measurements at the stereo spacecraft, you see that stereo A has a much more impulsive enhancement and fall off, whereas stereo B had a less intense, more gradual enhancement in the energetic electrons. And looking at the pitch angles, you see that stereo A had that really high anisotropy in these particles, and so there hadn't been much scattering. They really were well connected to that source, whereas stereo B had much less anisotropy. And so really what that's telling us is, even though from most of the way we would approach the problem of seeing, okay, who should be better connected, what we found is that actually stereo A was the one that would be better connected to this source, even though that's not at all what our typical mapping would have told us. And so that means that the transport of these flare accelerated energetic electrons really then does depend on the background solar wind structure, particle acceleration of the flare site, and mechanisms driving cross-field diffusion or other kind of field line scattering. And this then really does present this clear example of the importance that mesoscale variations can have on transport of energetic electrons from a flare site on the corona to 1AU. And so really, if we do want to be able to say, okay, we have this observation out at 1AU, where really are we connected to on the sun, and how well are we connected? We really do realize we have this large gap, and it really originates from the lack of our understanding of these mesoscale variabilities. And so for us, what we would like to do is better be able to sample this by having a number of spacecraft that are closer together and be able to have some of these events go off where you have this release of particles and see from spacecraft to spacecraft how this variation really seems to be happening. And so we would argue then again that really the way to go about this is through a multi-point approach. So what we also know is when you have the transport of particles in the heliosphere is that you get modulation then of that particle population itself. And so as energetic particles propagate along a field line away from an acceleration site, such as from the reverse shocks at CIRs, various processes such as adiabatic cooling and particle scattering can lead to a hardening of the lower energy particle spectra. And so kind of what you can imagine that is, if you're really close to that source, you would expect to have the solid line here, and as you get further and further from the source, you expect to have kind of this hardening and then rollover of those low energy particles. But what we've seen a lot in different studies is that this hardening has not always been observed either as often or as significantly as expected. And there's actually a series of Parker Solar Probe papers in the much closer to the sun that still don't really necessarily always see this hardening the way we'd expect to be seeing. And so to try to explain this discrepancy, there's been several theories developed, such as non-shock related acceleration and or modifications in magnetic topology. So kind of assuming these sub-Parker spirals where maybe the Parker spiral is more radial than one might expect because you're in the rarefaction region. And then so you might actually have a shorter path length than you originally expected. And maybe that's kind of why you're seeing less modulation. But at the same time as different theories being developed to explain why we don't necessarily see what we would have expected, there have been other studies that have come out that have possibly indicated that maybe there is actually as much as one would expect. And so there's a study by Zhao et al., which used stereo and ACE observations. And so what they did in this study is they went through and found a CIR structure where at stereo B, they observed a shock structure. And then when that CIR then co-rotated over to where ACE was, ACE did not see that shock structure. And so then they said, okay, well, if we assume that shock is forming somewhere between the orbit of ACE and the orbit of stereo B, then that would mean we have some small path length between the observer and the shock at ACE, whereas stereo B did see that shock. So it's actually kind of getting that kind of solid line distribution from the Fisk and Lee model. And then what they did is later on in the rarefaction region, they took an interval from stereo B to kind of be that long path length that, if you're stretching all the way out to that shock structure, then you're going to have more modulation. And what they found when they did this is that comparing the negligible transport to some small path length to a longer path length, they did get something very reminiscent of what one would expect. But of course, the main source of ambiguity here is that when that CIR structure got over to stereo A, it had actually evolved enough that they couldn't do this analysis anymore. There was enough temporal variability in that structure. And then that brings up the issue of, how robust then are all these comparisons if there is, higher order temporal variability. We do know that from observation to observation of CIRs, they do change. And so they're not really these static structures that just go around. And so for that, what we would say is what would be ideal then would be actually at a single point in time, have multiple measurements in the rarefaction region kind of throughout the CIR structure and in the rarefaction region, and look at that variability in the particle spectra to actually be able to say, okay, if we actually take a snapshot in time, what is the spatial variability we have depending on the path length out to the shock structure? So this then brings me to what are kind of more about our solution. So more than just saying we want 4 points at small spatial scales. So for the Helios concepts, again, our baseline mission does include 4 spacecraft put into an Earth trailing Helios geographic orbit with the kind of relative drift rate. So early in the mission, they'd be really close together. And as the mission goes on, they kind of span out so we can actually look at different scale sizes. And so what this allows us to do then is at any point in the mission, you'll have your 4 spacecraft with whatever at that point in the mission your separation is, and you have multiple things you can look at. First off, you can look at data track through the plasma structure. So if you were to have a CME go through and you have kind of it pass over all the spacecraft, you get these radial slices then through that structure at 4 different points, and you can then compare each of those points to kind of pull out any smaller structuring. You also have a data track through the magnetic structure. And so Joe Borofsky has some nice papers kind of pointing at, you do have that does give you a slightly different cut through the structure. And then that lets you then start looking at variability of those magnetic structures. You also then have, you're connected to, 4 different field lines. And so that would then map to 4 different points on the solar surface. And so that lets you at any point in time be measuring slightly different mesoscale variability that is coming both from the sun and then out through interplanetary space to the spacecraft. But then you can think of, then the sun's rotating underneath you. And so then you can think of, if things were a really clean picture, then you would see the same source at different snapshots as it kind of rotates underneath each of the spacecraft. And that lets you start looking at temporal variability of what might be coming off of the sun. So what all this then, for all the science we want to go after, what that really then requires us to have as far as instrumentation is we need to be able to measure the bulk solar wind, of course. We want to be able to measure the thermal to superthermal ion composition with high time cadence. So we're actually, for the thermal to superthermal ion composition, we're aiming for sub-minute resolution. We want to have superthermal to energetic ion composition, and we want to have energetic ion composition. And the reason that we keep repeating composition throughout all of this is one of the things we really want to drive after is when you have these mesoscale variabilities in your system, and that might drive differences in the acceleration, we want to look for differences in kind of your mass per charge acceleration to look at how these local variabilities might actually play into that. Additionally, we need to have the energetic, the low energy electron distributions. So that's what we want to be able to look at not only the core, but also the straw. And that's really important for you to detangle, if we're changing between different flux tubes, we expect changes in the straw of the electrons. And we also need to be able to see energetic electrons. So if we're really looking at these flares that go off and wanting to map those energetic electrons released, we of course need to be able to measure them. We also need to have, a DC magnetic field observations to know what the IMF direction is and variability within it. We need to be able to have AC radio electric field observations, look for, different types of radio bursts, as well as, again, being able to constrain, if things are locally seen versus on different flux tubes that have scattered into our flux tube. And we also want to have hard X-ray observations. And so this is really critical for being able to tie things back to the solar surface. We need to know when a flare does go off, both what the timing of that is, but also being able to characterize the energetic electrons in the corona. So this really is kind of our ability to connect the observations at 1AU back to that source. And for the hard X-rays, that would be likely on either 1 or 2 spacecraft due to the spatial scales we have. And so if we were to have it on 2 spacecraft, they'd be on kind of the bookending spacecrafts, so that as the spacecrafts get further apart, you might be able to use it to better characterize limb flares. But for all of our other instruments, we'd want to have these on all 4 of the spacecraft identical, so that we can really look for these variabilities. So as far as going beyond just what measurements we want, the next question is, are there instruments that can provide this? And so I should say, while we do have a mock payload, this of course is a very, for what this grant is funding us to do, we're doing a mission concept to try to feed into the decadal. We are not necessarily proposing this as a mission to fly immediately. And so all of these payloads are merely just to show that we do currently have the needed technology in the community. And as such, this could actually happen. But should this go to proposal, some of these, different teams propose different instruments. We're not trying to spin anything in a certain way to favor certain groups. But as far as bulk ions, the clear choice for this, since we're mainly caring about the bulk population, would just be to use a Faraday cup. And different institutions do have Faraday cups. We've been flying them for a very long time. They're a very proven technology. As far as the thermal ion composition, you could imagine something kind of like SWIX. And so I know that the mission group has been pushing more advanced versions of SWIX, and as well as other groups. And so really for that, what you'd want to be doing is use something like that to be able to go after the mass and mass per charge state of these more thermal ions, not focusing on the protons for this because that's going to be swept up in your bulk ion measurements, but really be able to look at variability in these different ion species. We want to have something like a superthermal ion composition. And so for that, there's multiple instruments. Here at APL, we have an iteration of superthermal ion spectrograph on Solar Orbiter that can go to a little bit lower energies, a little bit more angular resolution. And that would work for this purpose. But again, other institutions also have options. We want to have the energetic ion composition. So again, we have instruments like CIS. We have a larger version of CIS, can go to higher energies. You could also go to other institutions for other instruments as well. For low energy electrons, pictured here is SPAN B from Parker Solar Probe. But again, this is a proven technology. We've been able to measure low energy electrons for a long time. For energetic electron or electron ion instrument, you could do something like Solar Orbiter EPT as a good kind of mock payload for that, to be able to look at this kind of critical range of electrons we want to be able to compare back for these SCP events. For the X-ray, we could use something, since we want to have 4 spacecraft, we need to be thinking more compact. And for that, the Solar Orbiter 6 instrument is really lovely. And so you can have this indirect imager, so you not only know kind of what active region gave you the flare, and be able to characterize the flare really well, but also be able to kind of fit it in the form factor you need if you want to have 4 spacecraft. Fluxate magnetometers, many groups make these, flying them on everything. You always need a fluxate. And then electric field radio waves. And so for this, you could use either something like Solar Orbiter RPW, ANT, so antennas, or you could use stereo waves. So all of these instruments that we would need to make these measurements do exist in the community. And so this really is a feasible mission to go down. The next question that people often ask is why 4 spacecraft? So why both why 4 spacecraft as far as why can't you do this with fewer? Could you do this with only having 2 or 3 spacecraft? But also, will you have mission creep and suddenly demand 12 spacecraft? So why are we saying 4? And really what's motivating that is that 4 seems to be this kind of Goldilocks scenario, where if you assume that the structures you want to look at are going to have certain types of variability to them and have certain forms, then the question is, what would you need to actually be able to resolve that form robustly? And so if you were to assume, for example, a Gaussian variation, and so the dashed line here is a 5th order Gaussian. If you only have 1 spacecraft, you're going to have 1 value. And so that's kind of where we've been for most of our studies to date. And so it just tells you, at this certain location, this was your flux. And you could assume that for everything, but that's probably not a very good assumption. When you have 2 spacecraft, start getting gradients, but your lowest order gradients. And so again, there's a lot of, depending on where those 2 spacecraft are throughout the structure, you can get very different answers as far as what that structure might look like. Going to 3, you can start getting a little more complicated. Things start converging on our line a bit better, so you're constraining it better, but there's still a lot of variability and incorrect fits. Once you go to 4 spacecraft, though, you can do that 3rd order Gaussian. And what you see is that if you assume a 5th order Gaussian, so you have this offset at the bottom, what you see is that you do start biasing yourself a little bit on one side, but you're mostly capturing the structure very well and very robustly. Going to a 4th order Gaussian gets you better through the core. Your wings get a little bit more interesting because you allow for that offset, but it does look a lot better. And then, of course, when you have 6 spacecraft, you can resolve the 5th order Gaussian. But really, from what we would say is that when looking at all of these, really the 4 spacecraft is where you're getting the most bang for your buck. Going from 4 to 5 doesn't actually buy you that much more. Going down to 3, you definitely lose a lot. Now, while there are a lot of variations we expect that would be Gaussian or Maxwellian, or even if you want to go into kappas, while these functional forms are one thing we see a lot, another one is kind of more sigmoidal variation. So if you think about current sheet crossings, things like that, you might get more of a sigmoidal variation. And again, for 1 spacecraft, you don't get very much. You get a single value. For 2, you get a gradient, and so you get something that looks really neat, but isn't necessarily helpful for really constraining this. When you go to 3, you also get something that looks neat, but isn't well constrained. But then for a sigmoid, if you have 4 spacecraft evenly separated this, and so for this we kind of slid where they all were. As long as you're of relevant scale sizes within the structure, you actually can really well resolve the sigmoid distribution. And increasing spacecraft, of course, is always great, because then if you have more uncertainty, you can constrain it better, but it's again not really buying you that much. And so from these kind of back of the envelope analytical calculations, it really does seem that 4 spacecraft is that point where below that point you really lose a lot, and past that point, while we would all love for that, it gets harder to argue for each additional spacecraft. So the next question is, why now? Why is this the time when we really should be pushing for a mission like this? And what we would say is, fundamentally understanding the mesoscale structure of the solar wind and transients and its subsequent effects on particle acceleration and transport will be paradigm shifting in our vantage point and insight into the heliosphere, as mesoscale dynamics are critical in resolving long-standing questions in the community, such as structure, acceleration, transport. And so Heliodisk will fill an observational gap in the current HSO as mesoscale solar wind structure and dynamics fall between the global scales studied by in situ instrumentation on stereo and occasional opportune conjunctions in the HSO. So when you have all of our spacecraft nicely separated and you get these large longitudinal events, it's between that and the kinetic scales that have been unlocked by times in MMS and cluster or in the solar wind, or by comparing L1 constellation observations and the potential Helioswarm mission. But also right now is a really great time, because with coronal source mesoscale structuring soon to be resolved much better from the PUNCH mission, which will be able to start looking at these mesoscale variabilities much closer to the sun, Heliodisk being able to then explore it at 1AU really does allow us to leverage those observations and say, if we know that these are the certain scale sizes close to the sun that are relevant, we can then look at how much of that is changing between the corona and out to 1 AU. Is it really just volumetric expansion of the same mesoscale structuring, or are you introducing new mesoscale modes on top of that? And so with
Robert,
these
you have
new
5 more minutes.
Perfect. Thank you. So with these new observations coming online, this really will allow us then to leverage all those observations we have. And so as such, a new mission enabling multi-point architecture really is an essential to address these objectives. And right now really is a right time for us to start trying to fill in this long-standing gap. So for where we are now, so our Helios mission concept study proposal was selected, which I'm very excited about. And so our 2-page pre-study report can be found online at NASA's website. And so you can either go to that link or scan the QR code on the right. And so under this grant that we're receiving from NASA to do this study work, kind of our deliverables for this will be 2 white papers, one white paper on the science motivation that we're targeting, and another white paper on the mission architecture. And both those will go to the Heliodecadal Survey Committee. And also we'll do a full mission concept study report to NASA, which will be made publicly available. But with that, where we are right now, which is why I'm really happy to be talking to all of you, is that we are actively working on kind of focusing our STM and flow down to mission requirements in preparation for our actual full development study in early February. And so in a matter of weeks is when we're actually going to do kind of the mission design run to really kind of hammer out all the details of what would this spacecraft look like, how can we get all this to fit, and various things like that. So where that gets us to is really right now is a great time for input. So your feedback and suggestions on the concept are really important to us and really welcome. And so in addition to that, we'd also would love to coordinate on and join in and endorse white papers that are for mesoscale dynamic research going into the decadal. And to try to help with that, we have a Google form at the link below, as well as you can scan the QR code to the right. And all the questions on it are optional. So if you don't want to answer anything, don't. If you only want to answer one of them, great. But really what we're after is kind of hearing about what does the community think of this? Is there anywhere the community thinks that we're either definitely getting correct and need to stay on that topic, or possibly getting not quite right and you'd like to see some shift? But also, would the community at all be interested in either endorsing our white papers or leading white papers that they think that would be relevant that we might want to endorse? And so all of that, if you go to this forum and provide information, then we would be happy to help anyone else as well as have you help us. And so with that, that's all I have for this presentation. And so I'm more than happy to take questions and discussion now.
Okay, thank you very much, Robert, for your nice presentation. And we are now open for discussion and questions and comments. So please either unmute yourself or just raise your hand and ask question or make comments.
This is Jim Drake. Maybe I can ask a question.
Yep.
What you're proposing is 4 spacecraft which are really have a complete set of instruments on each one. Now, one can imagine an alternate scenario in which you only have one or a couple of spacecraft that are really fully instrumented with composition and all that sort of stuff, but then have a slew of more minor spacecraft, which, for example, could measure the magnetic field and simple measurements of particle energy or something like that. No composition, for example. And so did you go through a process in which you thought about the other options and then finally converge on what you have?
Yeah, so that's a good question. So we did think about that, and it has been brought up. One of the questions really is, whether or not we think we can get closure of our science goals without seeing the variability in composition. And so if you want to use composition as a tool to, for example, know input on if you're changing between different flux tubes, different source regions by looking at, alpha proton ratios or even changes in, your oxygen to iron ratios, things like that. Then in that case, only having one or maybe two spacecraft that have that ability does then start hampering you a bit. It is true that some of these science questions we have do not require that. And so it definitely would be a thing that, that could be viewed as a potential descope option, but you would, kind of the feeling from us is that you would lose quite a lot by giving up the ability to actually get the compositional information and to go the path of only really having basic plasma and field observations in addition to kind of a contextual, even if maybe you're not in the same flux tube, larger spacecraft.
But I guess what I was thinking was not a descope option, but another option in which you don't just have 4 spacecraft, but you may have 10 spacecraft with many of those spacecraft having many fewer instruments. So I'm not asking for a descope option. I'm thinking more of a in which you could get greater information about the structure at the same time.
So you're meaning like additive, where in addition to the 4 we have, you then have a bunch of daughter satellites to give you more smaller scale variability in the fields and
Well, I'm thinking of
base
daughter.
plasma.
I'm not thinking necessarily the same 4 spacecraft, but yes, daughter satellites which would provide fewer information. But if you're really trying to figure out, for example, the magnetic structure of these things, that you could really do a very good job if you had, say, 10 spacecraft spread out, looking, even if they had some pretty simple instrumentation, you could get a sense of what the magnetic structure is, and maybe some bulk flow measurements, a few energetic particles, but reduced set of instrument for each.
Yeah, I mean, I think as long as you are, so to make sure I'm not misunderstanding, I mean, if you were to have still multiple spacecraft with composition at the relevant scales, and you add to that a bunch of other spacecraft with more limited measurement capabilities, then I do agree. I mean, that would be really nice. I think for what we were looking at, we really did feel that we needed to have that kind of 4-point on mesoscale full suite. And if you wanted to add to that, then it kind of comes into a question of the added science versus added cost and complication. Because already, it's fun trying to do the packaging for the 4 we have.
Okay, thank you. Thank you for the discussion.
So this is Tango, and I can make some comments, I think. First of all, this is a very nice and very interesting mission, I think, should hopefully get supported. I think I partly agree with Jim that if you only have 4 spacecraft, you might not have a good mapping range, where you can get a very different multi-spacecraft measurement, so you can get a taste on what's really going on. But my comment is, on the other hand, I think, for example, for energetic particle variability at the shock, 100 Earth radius might be too far away, where you will have 4 very different profiles for energetic particles. And if you have options to make them closer, closer than, I think, maybe something like 10 Earth radius, maybe a little bit larger than that, it will be a good starting point, and then you can make your separation larger to tell the difference. My motivation is that 100 RE is a little bit too close to the correlation length of the turbulence in the interplanetary space, which is something on the order of 1 megameter, I think. So I'm worried that you will have 4 very different profiles, rather than you can have start from the same profile towards more different profiles. That's the comment.
Yes, that's a very good comment. And one thing we have looked at is trying to adjust to some of the different science questions, of course, all want different scale lengths. And so how you kind of balance that. We do know that from what we have been able to pull out, given you see the Poisson error bars here, so it's a grain of salt. But when you get to 100 of RE, you still have where in their study they'd be pointing to about 85% of the observations actually having very similar profiles. And even when you get up to 300, that's where it's dropping out to half. So I would agree that when we get to the point where we're much larger than that, it will start merging together. And I also agree, it would be really interesting if you actually could span this whole range. I do think that even at the hundreds of RE, we will still see sometimes where they'll be the same, and we still see, clearly we see when they're different. So with that though, I also agree that, for our nominal starting point, we are kind of missing this vantage point.
Yeah,
And so
that's also
one thing that would be nice is if we could start lower. I think then it kind of gets to, if we're okay missing some of the larger separations, we do want to get within the mesoscale range, because if you start here and you're still going to drift up to here in the same number of years, this scan is still going to be very quick relative to everything else. But that's
Yeah,
where what we're trying to target is, yeah. Go ahead.
my initial feeling is at least maybe a factor of 5 less than a megameter. A megakilometer will be at least from my concern, that will be a good strategy. For example, starting from 0.2 or 0.1 megakilometer will be slightly.
That's something we can look at.
Yeah.
Right now, we're planning on starting at 0.5 megakilometer, and so going down to 0.1 is something we can look at. So that's a good suggestion.
Okay, thank you.
Thank you.
Okay, other questions or comments?
Hi, this is Jung-Woo Lee.
Yeah, go ahead.
My question is about only magnetic field. It's not about future plan, it's whether such data exists. The turbulent spectrum that I'm watching now is that if we approach the sun, how this spectrum will change? Is there any data showing such a trend?
So you're asking how this spectrum changes as we go closer to the sun? Is that your
Yes.
question?
Yes.
I don't know the answer to that question. I would be curious if anyone's done that with Parker or maybe Solar Orbiter. Does anyone on the call know? Not sure anyone knows. That's a good question.
I think they have looked at this, but I don't know what the answer is to what they actually found. So I'm pretty sure they're looking at this, but I don't know what they found.
So my expectation is that will the characteristic scales appearing in this spectrum will be replaced by more like solar scales?
Yeah, I'm not sure.
Okay, are there other questions or comments? Yeah, I see that everyone is muted now. So it seems that like all questions and comments have been made. And let me again thank Robert for the presentation and bringing this concept into our attention. So thank you very much. And this,
Yes, thank you.
Because the webinar is closed. So thank you for attention.
Thank you. Bye.